Okay, Dr. Matthew J. Traum here. We've figured out the tolerance loop template for our O-rings and Burette interface on the Stopcock, and now we've got to run through the analysis. The one thing that I noticed as I had the camera turned off is I forgot to add a direction to my vectors, and so I'm starting at the center line, and my positive datum is moving up from the center line. So add that into your drawings. I forgot to do that. Now we're going to run through. Let's see if I can get it all in view here. There we go. We're going to run through how to set up the vector equations. Okay, this might be a superfluous step. But as you guys know, I like to do things, all completely and meticulously as I can, just to kind of know and remember where things came from. So if there are any kind of unusual surprises, I can identify them and deal with them as I'm walking through my analysis. Okay, so what I've done here is just sum up all these vectors following the vector math that you watch in the asynchronous video. So I've just added vector s plus or minus delta s to vector d plus or minus delta d to vector I plus or minus delta I and to vector b plus or minus delta b. And they're all positive, right? They all have a little plus sign sitting in front of them because the directionality information is contained within the vectors themselves. So hence these bars over the vectors. So that is kind of the general form of the vector equation. The next thing I'm going to do is going to write the scalar equation. And in the scalar equations, I'm going to drop the vector notation, and in so doing, I now have to keep track of the directions of each of the vectors. And so let me not put that in there yet. So I'm going to just write all of the scalar quantities by themselves. And then b plus or minus delta b, okay, equals 0. So I've intentionally not put pluses or minuses in here so that I can show you where they come from. So again, my positive datum is from the center line upwards, and so s was a positive vector. When I dropped the vector sign, I had to keep the plus sign sitting in front of it to keep track of its direction. D is also in the positive direction according to my datum, so there's a plus sign that would be sitting here. I goes in the negative direction with my datum, so there's a negative sign there. And then B is also in the negative direction, so there's a negative sign there. Okay, those are my scalar equations. Next thing I need to do is figure out I min and I max. So for I max, that occurs when I max is equal to I plus delta I. And so we know from before, we've got I is a 0.08 millimeters, and then it's going to be plus 0.055 or minus 0.045. And so I'm going to say this is 0.08 plus 0.055 millimeters. And if I do that, I get 0.135 millimeters. Okay, and then I min occurs when I min is equal to I minus delta I, and so that's going to be my same nominal dimension, 0.08. And then I'm going to subtract the negative bilateral unilateral dimension, which is 0.045 millimeters. And so that gets me 0.035 millimeters. Okay, so there's my I max and my I min. Now I can kind of get this out of the way. I have all the information that I need to just run through the math and get those unknown tolerances that I had in the previous video. Okay, so let's start out with the analysis for I min. Okay, so for I min, now again, I've got to look at the picture, and I've got to figure out, okay, for I min, how do I want the vectors and their tolerances to either sum up or subtract out to get myself to a min situation, and then get the plus signs and the minus signs that are sitting up here in the scalar equations from that analysis. Now, you guys know Dr. Nemi likes to run through and do each one individually, and I think, intuitively that's good to try to get a sense of how to do it. But if you're, in a rush for time, if you're doing this on an exam or something like that, there's a quick kind of workaround, which I've showed you guys, which is to just figure out one and work your way back from that one to make sure that all the signs line up. So that's what I'm going to do. Okay, so for I min, I know that to get the minimum interference, I need S minus delta S. And so that's going to then just sort of force my hand in all the other ones. So D minus delta D minus I min. I don't need to deal with that because I'm just putting those two guys together. And then minus B plus delta B, right? And this plus arises from the fact that B is going in the opposite direction, right? So to get I min, minimum interference, I want to make B as big as possible rather than as small as possible, whereas these guys want to be as small as possible for I min. Okay, and this equals 0. And so now I can just pull out the nominal dimension. So it's S plus D minus B is equal to minus delta S plus delta D and plus delta B. And I'll show you in a second how I got all that. And then this is equal to I min. Okay, so now here's a sanity check. All of these all these vectors all have to have the same sign sitting in front of them. So when you put them in a parentheses, you should have just one sign sitting out in front of that parentheses, and you should be able to distribute that sign all the way through, and it should be the same in all cases, right? So I've got a negative sign here, a negative times a positive is a negative, so that's fine. I've got a negative sign here, so a negative times a positive is a negative, so that's okay. And then here, I've got a negative sign out front, and it's multiplied by a positive in here, so ultimately this will be a negative sign, and again I have a negative times a positive, which gives me a negative, and so I can pull out this negative sign, sit it right here, distribute it across all of these. They're all the same sign, and so I just put a little check mark there to indicate that I've done that step correctly. I've got all of my tolerances pointing in the same direction, which is what I need to do proper tolerance loop analysis. So always good to check that in every single step. Okay, and then now I can plug in numbers. So S is 4.105, and D is 1.615, and B is minus 5.585. Remember, these are the numbers that I measured before, and I had to fudge them a little bit because the dimensions have changed very slightly. That's probably just an issue with the accuracy of the caliper. Delta B, okay, and then equals 0.035, right? Because I min is 0.035, okay? If I add these together, I get 0.135 millimeters. I'm going to leave delta S plus delta D plus delta B alone, and then minus 0.35. This is millimeters. Okay, now I'm going to subtract 0.135 from both sides, and I'm left with delta S plus delta D plus delta B is equal to, well, it would be minus 0.1, but I had a negative sign sitting here, so let's not forget that, minus 0.1. Okay, and in the end, then, I've got delta S plus delta D plus delta B is equal to 0.1. All right, and I'm going to just remind myself that this was the negative unilateral dimension for S, the negative unilateral dimension for D, and the positive unilateral dimension for B, in case I come up with different values for the other I max calculation. Okay, so we got that. Let's move on to I max now. Let me call this 2 prime so that I don't get it mixed up with my originals. Okay, now we are into Imax. So I'm going to do the same analysis, but I'm going to do it on the Imax side. So really, this is just the inverse of what I did before. So it's going to be S plus delta S plus D plus delta D, and then minus I now max rather than min, and then minus B minus delta B is equal to 0. Okay, right, and so just as a quick recap, the reason that I chose plus and minus is primarily because in the I-min analysis I chose minus and plus, right? So I'm just doing the opposite. So that's one way of thinking of it. And then another way of thinking of it is to go back to the original equation or the original drawing and say to yourself, okay, if S is as big as possible and D is as big as possible, I'm going to get the biggest interference as possible. And so that's my Imax situation. And so those are both positive, and then B has to be as small as possible to get the biggest interference possible. And so that one should be negative. So that's Dr. Nemi's approach. Okay. So now that we've got this guy, I can distribute through. So it's going to be S plus D minus B. So I'm just pulling out all of the nominal dimensions and putting them all by themselves. And then I'm going to have plus delta S plus delta D plus delta B is equal to I max. And the same story here. I'm going to do the sanity check to make sure. Plus sign, plus sign, plus sign, plus sign. Minus times a minus is a plus, plus sign. Good. Okay. So all my signs all line up in my tolerances, which means that I've done this step correctly. And now I can move on to plugging in the numbers. I'm not even going to bother with the numbers here because we've already done that calculation for I-min. I know that it's 0.135. And then here I've got delta S plus delta D plus delta B is equal to I max. Now, what is I max? Okay, here's my I max from before. It's 0.135 millimeters. Okay, and I now subtract 0.135 millimeters and 0.135 millimeters from both sides of the equation. Cancels here, and what I'm left with is delta S plus delta D plus delta B is equal to 0. Okay, so let me put this guy in a box, and let me dial back to my 2 prime, and I'm going to put this guy in a box. And the one thing that I have to remember is I'm going to look back here, and this is going to be S plus, right, because it was the plus side. This is going to be D plus because it's the plus side, and this is going to be B minus because it was the minus side. Okay, and clearly I'm going to have different different tolerances, unilateral tolerances, because the sum here is one value and the sum here is something else. And so ultimately I'm going to get a different value on the high side as I am on the low side, tolerancing those nominal dimensions. Okay, so what do I do now? Well, I start to sort of look at this and you're like, wait a minute, you've got like 3 unknowns in one equation and 3 unknowns in one equation, so you can't possibly solve for these. There's 2 techniques that allow us to solve these. One is called equal distribution. There we go. Senior moment. Equal distribution, and the other one is called equal precision. So typically, equal distribution is used when the order of the nominal dimensions is the same. And in this case, that's pretty good, right? These guys are, so we're talking about S, D, and B. We've eliminated I from our equation, so we don't need to worry about the size of I. That's already set based on the Parker O-ring catalog. And so I'm looking at S and D and B. S is 4, D is 1.5, 1.6, and B is 5.5. They're all the same order of magnitude, and so I'm going to go ahead with equal distribution. Other possibilities, equal precision, and you would use that if you have dimensions that are nominal dimensions that are different orders of magnitude, but that's not our case here. Okay, so I'm going to just set them all equal to each other, and so this is pretty easy, right? It's delta S plus is equal to delta D plus is equal to delta B minus is equal to 0, right? So we have no room to maneuver in those dimensions for S plus, D plus, and B minus. Okay, let's do equal distribution for our I min case. Now, so remember for I min, we had delta S minus plus delta D minus plus delta B minus was equal to 0.1 millimeters. I'm going to use equal distribution again, and so I'm going to do there is I'm going to say, okay, delta S minus is equal to delta D minus is equal to delta minus, which means that if I look back up at this equation, that delta S minus is equal to 0.1 millimeters divided by 3, and that's also equal to delta D minus, and it's also equal to delta B plus, right? Because each of these is now the same tolerance, and so if I just solve for one of those, I get 0.1 over 3, 0.1 millimeters over 3, and they're all the same, right? So no problem there. Okay, so if I actually do the math, I get delta S minus is equal to 0.033 millimeters, delta D minus is equal to 0.033 millimeters, and delta B plus is equal to 0.033 millimeters. Okay, so last step then is I want to write the nominal dimensions and their tolerances. So S is, if I go all the way back to the beginning, right, S is 4.105, and then it's going to be plus or minus. Plus is going to be just 0, and S minus is going to be 0.033 millimeters. Okay, that's S. D, same way. I'm going to go back and look at the value of D, which is 1.615. So 1.615 plus or minus, okay, plus D. D plus is 0. D minus is, where is it? There it is, 0.033. So, right, bilateral dimensions, unilateral millimeters. And then, what am I missing? Oh, B. So B is equal to, from my original table here, 5.585, and then plus or minus. And now I have to be careful because they're reversed, right? So B minus was 0, and B plus is 0.033 millimeters, right? Okay, there we go. So now I've got my nominal dimensions and my tolerances all set up to enable me to plug them in here if I wanted to tell me what the tolerances in those dimensions need to be to ensure, at least according to the Parker O-ring handbook, that I'm getting an appropriate interference fit between the static O-ring and the Burette wall to facilitate an appropriate pressure for a seal. Okay, that's the end. Thanks for your attention, and look forward to seeing you guys in class. Thanks. Bye.